Now, when you're talking about electrical circuit normally involves a charge that moves through a circuit. It goes around in a loop. All right. So there are comparisons that you can make between the flow of charge in an electrical circuit with the flow of water inside a pipe system. Okay. You can make some similar comparisons. So let's go with something that's more familiar first for the case of water flowing through a pipe system. So let's just say right now we have a pipe system that looks like this, and there are three different levels: level A, level B, and level C. And then we start from here. Okay. So what we'll say here is that whenever you have water at levels A, B, and C, either here, here, or here, they will have different values of GPE because you understood that they are at different heights. So if you have water that flows from A to B and then from B to C, what will happen is that there will be decreases in GPE because there's a decrease in height. The water is actually losing energy here. Now, the fact that that water, or rather that mass of water, is losing energy, that one is actually comparable to PD in an electrical circuit, which we will see later. Okay. Now, at the bottom, when water is pumped back from level C back to level A, there will be an increase in GPE here. The water will actually gain energy as it moves from C back to A. In order for it to move from here to here, you need to put energy in. The water is gaining energy, and that energy that is gained is actually converted to increases in GPE. Now, this one will be comparable to EMF inside a circuit. All right. Now, the flow of water inside the pipe is comparable to flow of electrical current. Any obstructions in the pipe that slows down the water flow is comparable to electrical resistance. All right. So this one is what you expect to see for water flowing inside a pipe system. So now, if we look at the case of electrical circuit, specifically for the case of a charge that is flowing through an electrical circuit, let's just consider you have a charge of Q. All right. So that charge of Q will actually move through your circuit like this. Oh wait, sorry, this is not a good color to use. That charge Q that you have will move through the circuit like this. All right, it will move around the circuit, making one loop, and then come back to the battery. So what we'll say is that the charge, once it passes through the battery, it gains electrical energy when passing through it. This causes it to have an increase in electrical potential. All right, kind of like the case just now when we say that your water, when it went from the bottom to the top, there's a gain in gravitational potential energy. So over here, when your charge went through the battery, there's actually a gain in electrical energy, which causes its electrical potential to increase. All right. Now, as it moves through the circuit, what will happen is that, assuming that no resistance is encountered, note the potential remains unchanged. So what we mean by that is that if, let's just say, the charge was here, and then after that it moved past the battery, it already gained electrical energy. All right. So this charge here is at a certain potential. Now, provided that when it moves from here all the way to here, there's no resistance, we'll say to you that the potential is constant. All right. So over here, it's already mentioned that once the charge passed through your battery, it was already at a potential of 12 volts. So from here all the way to before the resistor, assuming that there was no resistance, the potential ought to remain constant. All right. It's only when it encounters some sort of resistance, like going through a resistor, that your charge will start to lose electrical energy. So your charge moves from here to here. It already gained electrical energy here. The energy that it has remains constant all the way to here. But then once it wants to pass through the resistor, it will start to lose electrical energy. Okay, you start to lose electrical energy, which in turn causes it to have a decrease in electrical potential. So if before the potential was 12 volt from here to here, suddenly over here you start to lose electrical energy. You start to lose electrical energy, you will have a decrease in potential. So your potential will drop from 12 volts to 4 volts. Okay. Then after that, your potential remains constant here. And then once it goes through your resistor, again, it loses electrical energy. You lose electrical energy. Electrical energy is lost. So but again, your potential drops. So after you pass through the second resistor, your potential is actually 0. Then it remains that way all the way to the start of your battery. Okay. So one thing to note here is that when it comes to differences in potential, EMF is the difference in potential between 2 points where charge gains electrical energy. It's actually this part here, which you will normally term as EMF. It's because between these 2 points, the charge is gaining electrical energy. Other forms of energy are converted to electrical, which in turn corresponds to an increase in electrical potential. Before your charge went through your battery, it was at 0 volts potential. But then after it went through the battery, the potential increases because it gains electrical energy. So your potential could have increased to 12 volts. But then when you look at the difference now between these two potentials, this is 12 volts, right? This is your EMF, okay? The same thing could also be said for PD, all right? PD is difference in potential between 2 points where charge loses electrical energy, corresponding to a decrease in electrical energy. So if you look at PD, that one will be these portions here. So when the charge was here, it was a potential of 12 volts. But then once it passed through the resistor, it lost electrical energy. It was converted to heat energy or heat dissipation. So when the charge came out of the resistor, it already had decreased potential due to the fact that it lost some electrical energy. So the potential is now 4 volts. All right. So these two differences in potential is actually what you know as PD. Okay. The same could also be said for here. This one is also PD. All right. PD, EMF are basically just differences in potential between 2 points. But one is different in the sense that if it gains electrical energy, which causes it to gain electrical potential, that is EMF. And then the other, if you see that there's a decrease in electrical potential due to the fact that it lost electrical energy, that is PD. Okay, so this is what in simple terms happens to a charge inside your circuit. All right, so now we go back to page 1. All right, page 1. Now, we'll go through all the different terms like current, voltage, and resistance. Now, the first thing you would learn is current I. All right. Now, when you're talking about current, before we go to current, we need to talk about charges first. Now, all charges that exist naturally are actually whole number multiples of an elementary charge, E. An elementary charge E is 1.6 times 10 power 19 coulomb. Now, all charges that you can see occurring naturally will always be whole number multiples of an elementary charge. What it means is something like this. Your charge could be, say, 1.6 times 10 power minus 19, or 3.2 times 10 power minus 19, or 4.8 times 10 power 19. You see, in terms of the elementary charge E, this one is E, this one is 2E, and then this one is 3E. Okay, whatever charge that you see existing in nature, they must be in terms of whole number multiples of your elementary charge. If say, for example, I have a charge where it is, say, 2.8 times 10 power minus 19, or something where I say it is 6.0 times 10 power minus 19, in terms of your elementary charge, Right, this is 2.8. Okay, 2.8 is actually 1.75 of E, and then 6 is actually 3.75 of E. So in cases like this one is not possible. Only this one is possible. This one is considered whole number multiples of E. All right, all charge that exists in nature must be in whole number multiples of E. All right, they cannot exist in fractions like this. This is just not possible. All right. All right. So this one is actually what you will learn this as quantization of charge. This is known as quantization of charge. Sometimes your exam question, they will ask you explain what is meant by charge is quantized, or what is meant by quantization of charge. Quantization of charge actually just means this. All charges are actually just whole number multiples of an elementary charge. Okay. Now, then we move on to another thing, specifically to current. Now, if you have a flow of n number of charged particles or charge carriers, where each particle carries a charge of Q, the total charge carried by the particles will be Q, capital Q. Okay, there's a small q here and a big Q here. This small q here is the charge carried by one particle. The big Q is the total charge carried by all the particles. All right, and your number of particles is n. All right, now these charged particles can be electrons, protons, or alpha particles. When these particles form a net flow, if you have a net flow of charged particles in a particular direction, what we will say is that you have current. You must have a net flow of charged particles in a direction in order to say that there is current. Now, current is defined as the rate of flow of charges. So I is total charge divided by time taken. And then just now I mentioned that total charge Q is actually the charge carried by all the particles. So you take the number of particles n multiplied by the charge of one particle. That's why you get nq here divided by t. All right. Now it's from this expression here that you will be able to find something called the number of charged particles per unit time that is flowing. So what you do is that you are actually just looking at I equals to nq over t. You rearrange it, you get n over t, I over q. All right, this one will give you the number of charged particles per second, right? Because n is number of charged particles, t is time. So this is number of charged particles per unit time. All right. Now, if your current is constant, charge is QIT, taken from here. All right. If you want to find out the amount of charge, provided the current is constant, Q is IT. Now, it's from here that you can define your coulomb. All right. Charge is measured in coulomb, current is measured in ampere, and then time is measured in second. You could say that 1 coulomb is the charge that flows past a point when the current of 1 ampere flows for 1 second. All right. Now, on the other hand, if your current varies, Q is not IT. Okay, here we say that Q is IT when current is constant. If you encounter a case where current varies, then Q is actually the area under the IT graph. What we mean by that is this. If let's just say that you have a graph of I versus T that looks like this, all right, if you have a graph of I versus T like this, you see that the current is varying, it's not constant. In cases like this, your charge is the area is actually half IT. This one is not non-constant current. All right. If you have constant current, okay, you have constant current, you get something like this. I versus T. Constant current would mean something like this. Okay, it's actually also still the area under the graph in general, but here what you get is Q is area under the graph is actually just IT. That's why we can say that only for constant charge, sorry, only for constant current, that charge is IT. If your charge, if your current varies, like this one, you would have to take the area under the graph. Right here, this one is a triangle. So you can actually find the charge as area under the triangle. Or if let's say we give you something else that's a bit different, like this I versus T, and we give you some sort of regular shape like this. This one you cannot really calculate it out. This one Q is just area under the graph. Okay, so this one you will normally see more under the very old past years. This one I think is before 2000. The recent ones don't normally test this anymore, but it's still something you need to know. Okay, right, so this is current. Now we go to direction of current flow. So I'll clear everything here. Right, now when we say current flow in the chapter, the current flow that we're always talking about is conventional current. All right, conventional current always follows the direction of flow of positive charges. It's always from positive terminal to negative terminal. All right, it will be useful to know that current always flows from higher potential to lower potential. All right, I think I wrote it here somewhere. No, I did not write it here. Okay, wait, let me just get this. Let me clear off this thing here. Right, direction of conventional current follows direction of flow of positive charges, which is always from positive terminal to negative terminal. What we'll just mention here is that current always flows from higher to lower potential. Okay, the reason why current will always flow from positive terminal of a battery to negative terminal of a battery is mainly because it tends to flow from higher to lower potential. In AS, you won't really make use of this information, but you make use of this information more in A2 later on. Okay, so if you're talking about conventional current or current right now, we're always talking about the flow of positive charges, which is from positive terminal to negative terminal, or from higher to lower potential. Okay, so we also have something called flow of electrons to consider. But when you're talking about flow of electrons, flow of negative charges like electrons, they will always be from negative terminal to positive terminal. In other words, always just think of this way, always just think of it as this. Negative charges will always be flowing in the opposite direction to conventional current. Okay, conventional current is flow of positive charge from positive to negative terminal. Flow of negative charges like electrons will always be the direct opposite. It will be going from negative to positive instead, or in other words, it's opposite to conventional current, opposite to flow of positive charges. So right here, what you have, if you look at the diagram, this is your battery. Okay, your flow of conventional current is actually from the positive terminal to the negative terminal. So you see it going like this, like this, like this, like this, like this, like this. Okay, this is flow of conventional current. But when you're talking about the flow of electrons, electrons will be opposite. You will see it as these red colored lines here. Okay, they will flow from negative terminal to positive terminal, opposite to flow of positive charges. So this is for current. Okay, now from current, you also have some other equation that relates to it, which is this one. I is equals to ANVQ, where we tell you that there's this little v here that is called drift velocity or drift speed. Okay, now you need to know the derivation of I is equals to ANQV, and this one was added from 2016 onwards. It's actually quite a recent addition to your syllabus. All right, Okay, so let's start with this one. Now, in any conductor, there will always be large number of conduction electrons or free electrons as there are atoms which form your electric current. Now, number density n is the number of free electrons per unit volume. Okay, so when we ask you to define number density, always remember that number density is number of free electrons per unit volume. If you define number density as just number of electrons per unit volume, this one is not accurate. You always need to write the term free electrons, because when you say number of electrons per unit volume only, the electrons could refer to the fixed electrons orbiting around your nucleus and also the free electrons. So it's better to be specific. Just say the free electrons, the electrons that are responsible for your electrical conduction. All right, always remember to add the term free electrons. If you don't, it means that you're saying the electrons here, if you say number of electrons per unit volume, you're referring to both fixed and free electrons. Okay, so you want to single out only the free, you just write the term free electrons. Okay, now this small n that you see here looks like the small n that you saw in the previous page. Okay, bear in mind that this is not talking about the same thing. All right, in the previous page, the small n refers to number of charged particles, but the current one, small n, refers to number of charged particles per unit volume. Which one is it? You will need to read carefully from the question. Okay. In your case, small n is number density. All right. Now, how do you derive the equation I is equals to AN QB? First, what you do is that you consider a section of wire of length L and cross-sectional area A with number density N, for which electron flows through. This is your wire. Okay, it has a length of L and has a cross-sectional area of A, and it has a certain number of it has a certain value of number density. So what we'll say here is that when current flows, electrons will move through the section with an average drift velocity in a time of t. Now, what you need to know from here is that for this given section of your wire, the number of electrons that you could possibly have is actually your number of electrons per unit volume, which is your number density multiplied with volume. Because you see, n is number of electrons per unit volume. So if you multiply with volume, you're going to get the number of electrons. Okay, so that one is NV. And then from here, total charge would be your number of electrons, which was NV here, multiplied with the charge of an electron Q. Okay. If you want to find out the current through this section, current, as I mentioned, is actually your total charge divided by time. Total charge is a capital Q divided by T. So your total charge Q is given here already. Number of electrons NV multiplied with Q. That's why you get this. NV times Q divided by T. All right. And volume is actually area times length. If you take the cross-sectional area A, multiply with the length, volume is product of area times length. So V can be expanded to become AL. So you get N times AL times Q divided by T. Then you rearrange one of the things again. N times A times L over T times Q. L over T is actually distance over time. So it's actually referring to speed. So this speed here is actually your drift velocity or drift speed. Okay, so eventually you are gonna get I is equals to AN dq. Okay, so this is the equation that relates drift velocity to speed. Now this equation applies to all charge carriers that form a current. It's not just applicable to electrons. It can be any other charge carriers that move. It could be other positive and negative ions also. All right? So it doesn't just apply specifically only to electrons. It applies to other charges too. Can be positive or can be negative, right? So this one is for current. Okay, then we go to the next property that you need to know, which is voltage V. All right. Now voltage are normally distinguished according to the energy transfer that occurs to the charge as it flows around the circuit. This one is similar to what I explained earlier, the analogy just now that I gave you. All right. A voltage where charge is losing electrical energy corresponding to decrease in electric potential is potential difference. Potential difference by right is defined as electrical energy converted to other forms of energy per unit charge. If you are asked to define potential difference, the statement in yellow is the definition to use. This is the formal definition. Okay, electrical energy converted to other forms per unit charge. So PD is energy converted to electrical energy converted to other forms per unit charge. Okay, this one here is not the formal definition. This one is more like for you to understand why is it like that. Okay, so a charge that loses energy corresponding to a decrease in electric potential is potential difference. Now, on the other hand, if you have a voltage where charge is gaining electrical energy corresponding to an increase in electrical potential, that is electromotive force, EMF. Okay, electromotive force, EMF, is defined as other forms of energy converted to electrical energy per unit charge passing through it. So EMF E is equals to other forms of energy converted to electrical per unit charge, right? Again, this is the formal definition that you should use if you're asked about EMF, okay? So as I mentioned to you earlier also, PD and EMF are really just differences in potential between 2 points in a circuit, whereas value of potential is actually value of at a single point. All right. So if we were to consider movement of 1 coulomb of charge around the circuit right now, like this one here, I have 1 coulomb of charge that moves through the circuit like this. 1 coulomb of charge that moves through the circuit like this. So when you have the charge moving through the power supply, electrical energy is transferred to the charge. So this part here is actually here. This part here is where your charge gains electrical energy. All right. Then the charge will flow through the circuit, transferring some electrical energy to the first resistor, and then the rest to the second resistor. So if in the example of the circuit here that you have, when it was at the battery, it gained 12 joules of electrical energy. So as it moved through the circuit, it encountered the first resistor, and then from here, it starts to lose some of its electrical energy, minus 8 joules, okay? So, and then it continued to move until the second resistor here, it lost more energy. This time it lost 4 joules, okay? So during this time when it kept losing energy and gaining energy, electrical energy specifically, that is what causes you to have changes in potential. So what I could say here is that if my EMF was 12 volts, if over here my EMF was defined as, sorry, let me just change the thing later. My EMF was defined as 12 volts. It means that the difference in potential between the 2 points across the battery is 12. So if I want to look at value of potential, this one could have 0 volt potential, whereas this point here could have 12 volts potential. It's the difference in these 2 points that gives me 12 volts. And because between these 2 points, my charge gains energy, gains electrical energy, corresponding to an increase in electrical potential. That is why we call it as EMF. Then as your charge continues to move here, your potential is constant. 12 volts potential is constant. All right, until here. So this one is 12 volts potential again. So once it passes through your resistor, it loses electrical energy, is converted to heat because resistor dissipates heat. It will lose its electrical energy. You will lose electrical potential. Okay, so since here they say that your PD is 8 volts, that means the difference between these 2 points is 8 volts. If this is 12 volts potential, the potential here should be 12 minus 8, giving you 4 volts potential. And then from here, since you didn't encounter any resistance whatsoever, the potential is constant until such a point that you encounter another resistance, which is here. So your charge passes through here, it loses electrical energy again. You will have decreased electrical potential, but how much is it decreased by? You see that here is 4 volts. So if this is 4 volts potential, and the difference here is 4 volts, it follows that your potential here would be 0. Okay, so from here all the way to here, your charge is having a potential of 0 volts. So this is 0 volts potential constant. All right, that's what EMF, PD, and potential actually is. Okay, so the thing that I just explained is actually also kind of explained here. All right, so you move to the next page, page 4. Now, there's this thing about voltmeters that I also kind of need to explain to you. Now, voltmeters, you know, it measures voltages. Okay, that is what we know. Voltmeters measure voltage. But what voltmeters actually do is that they measure difference in potential between 2 points in the circuit. That is what it actually does. It is measuring the difference in potential between 2 points. Okay, and now voltmeters by themselves do not require a current to function. Okay, so a voltmeter usually does not have current through it. If you're talking about an ideal voltmeter is supposed to have infinite resistance so that no current flows through it. Okay, voltmeter does not want current to flow through it. Okay, that is one thing that people need to understand first. Voltmeters do not need current to function. You don't need a voltmeter for the voltmeter to work. Sorry, you don't need a current for the voltmeter to work. It can work just fine without a current. Okay, now that being said, I say that a voltmeter does not need current to function. Okay, it doesn't necessarily always mean that when there's no current flowing, you're going to get 0 reading in your voltmeter. Okay, this one here is actually quite important to know. All right, if there's no current flowing through your circuit, it won't always be the case that your voltmeter reading is 0. Your voltmeter can give you a non-zero reading even when there's no current flowing through the circuit. Okay, so the example to illustrate that will be the diagrams here. So just remember for now, current does not flow through voltmeter, it's not supposed to, and voltmeter is really just supposed to measure differences in potential. Okay, so let's look back at this diagram here. Look at the diagram on the left. You have this circuit here, like this. Okay, we tell you that this circuit has an EMF of 12 volts and a PD of 8 volts and 4 volts. Okay, this one is your EMF, this one is your PD, and this one is your PD. Okay, so I have a voltmeter that is connected across this point and this point. It's measuring the differences in potential here. Since my EMF is 12 volts, obviously it will measure 12 volts. And then you look at the other voltmeter. Voltmeter 1 is connected between these 2 points. It's measuring the differences in potential between here and here. But since my PD is 8 volts, this one, my voltmeter reading will read 8 volts. And then you look at the second voltmeter, it's connected between this point and this point. It's measuring the differences in potential between these 2 points. But then the PD here is 4 volts. So the difference that I measure here must be 4 volts also. Okay. Now, of interest to you is this particular voltmeter. Okay, maybe I use a different color. Use blue color maybe. Okay. Of interest to you is this particular voltmeter. You say where is it connected to? It's connected here and here. All right. Now in your case here, this circuit has current flowing. Okay, wait, let me just draw the stuff here. This current is okay. This one is a normal circuit that is closed. You have current flowing here. Okay. Now this voltmeter here, the blue color one, VP, is connected here and here. So what do you suppose will be the voltmeter reading? Just now I gave you the example where I told you the potentials, right? So this one, the difference is 12 volts potential. Here, maybe I use green. Here was 0 volts potential. Here was 12 volts potential. And it remains constant all the way to here. Okay. It's only after it passes through the resistor that your potential will drop. Okay. So if your PD here is 8 volts, your potential here, what color can I use? Your potential here would be 12 minus 8 giving you 4, right? Here you will have 4 volts potential. Okay, but it will be constant from here all the way to here, right? Because you see you don't have any resistance in between. There's nothing that causes your electrical energy to drop. Okay, so you see here 4 volts, here will be 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 4 volts. Basically throughout this entire length, it's always going to be 4 volts. So if you have a voltmeter that is placed here and here, the differences in these two potential is actually the same. 4 volt and 4 volt, there's no difference between them. So it's just going to be 0 volts. Okay. So after here, 4 volts, you have a PD of 4 volts here. You have a difference in potential of 4 volts across here. 4 volts minus 4 gives you 0. So you're going to get 0 volts potential here. And then it will be constant all the way to here. Okay. So now you see there's some contradictions here. There's current flow, but your voltmeter reading is 0. Okay. So now what happens then if I have that same circuit, but this time I do something to it, where I tell you I break the circuit apart. This one, the circuit is already broken in the middle. Okay. So this one is broken connection. Let's just say that this is your broken connection. All right. So now, if there's broken connection here, okay, this one was closed circuit, got current flow. This is now open circuit. Okay, this is now open circuit because there's some broken connection here. For open circuit, no current flows. So here, I know that I have EMF of 12 volts. Okay, no current flows through here. Now, no current is flowing. What would be the readings for my voltmeter? Voltmeter V1, voltmeter V2, and voltmeter VP. And also voltmeter V0. Okay. For voltmeter V0, your difference in potential here and here is actually just going to be 12 volts. Your voltmeter is measuring the difference in potential between your across your battery. All right. So I could say that this one is 12 volts potential, and then this one here is 0 volts potential. Okay. Now, when it comes to your circuit having 12 volt potential here, previously I said that your potential is, if you look at the previous diagram, I said that your potential is only, your potential of 12 volts was only constant up to the point before your resistor, right? It's after the resistor that your potential start to change because you lost electrical energy. Now, in your case here, your potential is constant also. Okay, wait. The potential is constant also, but it will be constant all the way to here. Okay, maybe I use red color to illustrate the point. Your potential is constant all the way to here. Okay, this one will be where your 12 volt potential is constant. All right. Now, why is it that I say that there's potential constant all the way to here? Why isn't there a change in potential across the resistor? It's because you remember how PD is defined. PD is difference in potential between 2 points, where we say that the electrical energy is converted to other forms of energy, correct? PD was defined as electrical energy converted to other forms of energy, or I also explain it as when you have a charge that passes through a resistor and you lose electrical energy, that corresponds to a decrease in potential, right? That difference in your potential is your PD. Now you look at how charge flows. Is there even any charge flowing in the first place for an open circuit? In an open circuit, there's no charge flowing because there's no current flowing. So you're talking about the resistor here right now. There's no charge flowing through it. There's no current flowing through it. So there's actually no such thing as electrical energy being converted to other forms here. No such thing as electrical energy being converted to heat here. So since there's no conversion of electrical energy to other forms right now, your potential by right should remain constant. Okay, so that's why we say here across your resistor the potential remains constant. Okay, so maybe I better just write it here. No current flows through the resistor, so there is no loss in electrical energy. There is no conversion or loss of electrical energy of charge. Therefore, no PD. Okay, there's no conversion or loss of electrical energy of the charge. Therefore, no PD. Okay, therefore, also you can say this lah. There will be no differences. There will be no differences in potential across resistor. Okay, no PD, no differences in potential across the resistor. So now if we ask you what is the value of your voltmeter reading at V1, this one will actually just be 0 volts. Okay. Okay, now then after that we look at V2. Right, we look at voltmeter 2. Now your potential remains constant at 12 volts up to here. If you look at the other side, this part was 0, right? Your potential again will remain constant up to this point. Okay, here we'll tell you that up to here, 0 volt potential is constant. Same reasoning lah, because you see no current flow, no charge flow, there is no change or loss or electrical energy whatsoever here. So you do not have any PD. So PD here would be non-existent. Okay. So no PD, no change in potential. If I have a voltmeter across here, I will be getting a 0 volt. Okay. So maybe it's better I just write out the potential values. Okay. Here is 12 volts potential. Here would also be 12 volts potential. And then over here is 0 volt potential. Over here is also 0 volts potential. Okay. So you see 0 volt, 0 volt, obviously this is 0. 12 volts, 12 volts, obviously this is 0. Okay, now the last one, VP. This one. Now VP is connected across here and here. So remember I said that voltmeter doesn't need current to function. Voltmeter actually just measures differences in potential between 2 points. So for VP right now, which is connected here and here, it is measuring the difference in potential between these 2 points. This one is 12. This one is 0. So the potential difference, or the difference in potential, is actually 12 volts. Okay. So notice the difference here between this one and this one. This one, you have current flowing, but you're not getting any reading in the voltage. And then this one, you don't have current flowing, but you're getting some reading for the voltage. Okay. It's more like you looking at the diagram and seeing how the potential changes. Right? So this is for voltmeter. Okay, then after that, I move on to one of the last parts, which is resistance. Okay, so just bear with me again. All right, now we go to resistance. This is one of the last things that we have to do. Okay, now resistance. Now, when a battery is connected across a conductor in a closed circuit, charge carriers in the conductor will gradually move towards one end of the conductor as current flows. All right. The motion of these charge carriers through a conductor is often opposed or resisted by the conductor as they collide with one another or the atoms of the conductor. The charge carriers, when it wants to move from one end to another inside your conductor, they will either collide with themselves or they will either collide with the atoms of the conductor. So this slows them down, or their motion is being resisted. Okay. Now resistance is the measure of the opposition to current flow in an electrical circuit. Resistance is defined as the ratio of PD to current. Okay, so R is equals to V over I, where R is resistance, V is PD, I is current. Now, it is very important for you to know the differences between ratio, rate of change, and something per unit something. By now, you probably have gone through a few of these quantities. Let me just write them out for you. Now, if I give you density, this one you will tell me is mass per unit volume. Okay, this one you will tell me is mass per unit volume. Okay, now then if I give you, say, velocity, this one you will tell me is rate of change of velocity. Okay, then after that, if I give you Young's modulus, this one you will say is ratio of stress to strain. Okay, now notice the similarity in the equation form. Density is mass divided volume. Velocity is displacement divided by time. Young's modulus is stress divided by strain. Okay, Equation wise, they seem the same because it's something divided by something. But then when you define it, notice the pattern in which they're defined. Density was mass per unit something, whereas velocity was rate of change of something. And then Young's modulus is ratio of stress to strain. Okay. Now specifically between these two, rate of change of something and ratio of something to something, this one determines how your graph is analyzed. Okay. Um, this one will determine how you analyze your graph. Because if I tell you right now, I give you a graph of velocity versus time, sorry, displacement versus time. Say if I give you a graph of displacement versus time, and I tell you that you have a graph like this, okay, I tell you have a graph that looks like this, and then I ask you, what is the velocity at this point? What you would say is that, or to find the velocity at this point, you will get the gradient of the tangent, right? So velocity here, you will say, is because it's defined as rate of change of displacement, is the gradient of the tangent of your velocity time or your displacement time graph. Sorry, maybe I better just write this in a different color. If you have a graph of displacement versus time here, because velocity is defined as rate of change of, sorry, oh, this one is not velocity, my mistake. Rate of change of displacement, right? Rate of change of displacement. Because velocity is defined as rate of change of displacement, if you have a graph like this, if I ask you what's the velocity here, because it's defined as rate of change of displacement, it will be the gradient of the tangent. Okay, V here will be gradient of tangent because it is delta S over delta T. This one here being your delta T, this one here being your delta S. Okay, so this one is if something is defined as rate of change of something, you automatically tend to relate as gradient of a tangent inside your graph. Okay, but now when it comes to resistance, resistance specifically is defined as ratio. Okay, it is not defined as rate of change of PD to current. All right, it's not defined as rate of change of PD to current. So if say you were given a graph of say velocity versus time, like the ones that's being shown here in your notes, and I tell you the variation of your velocity and current is this, and then now we ask you to find the resistance at this point, you cannot use gradient or tangent. Okay, using the gradient or tangent at that point, at this point is incorrect because it's not defined as rate of change or PD to current. It's defined instead as ratio of PD to current. What you would have to do actually is that at this point, you have to find out what is the value of, at this point specifically, you will need to find out what is the value of V. You will need to find out what's the value of I. Sorry, I write it in proper coordinate form for you. You need to find out specifically what is the value of I, what is the value of V, and then find the ratio between those two values. Okay, that is what this one is trying to tell you. This point here, you need to specifically know the value. You cannot just find the gradient or the tangent like this. This is wrong. Okay, so to find the ratio of values at this point, I said that you cannot use gradient or tangent, but there's an easy way to find the ratio value. You can use gradient, but you have to use the gradient from the origin. Okay, let me just wipe off certain stuff. You want to use gradient, you can, but don't use gradient or the tangent. You need to use gradient from origin instead to that point to find the resistance. The reason why we say that is something like this. If you look at the graph at the bottom, this one is the same PD to current graph. I again want to find out the value of resistance here. Okay, I again want to find the value of resistance here. I cannot use the gradient of the tangent, but I can use the gradient from the origin. What I mean by that is that just draw a line from the origin to that point and then find the gradient of the tangent. That one will be your ratio already. Because what I will tell you here is that gradient from origin to that point is actually numerically equal to ratio of PD to current at that same point. Now, why do we say this? Is because if you look at this thing just now that I drew, just now I drew this thing here, right? If this one was value I, this one was value V, the resistance is the value of V divided by I to find the PD, okay? Right, this is what you see. Now say in this diagram here, let me give some value to you. This one is 0, and then this one is I, and then this one here is V. Now, if I want to find the gradient of the origin here, if I say just by using ratio itself, R is V divided by I, the value of V that I have here divided by I, okay? But if I use gradient from origin, notice that it will be V minus 0 and then I minus 0, which in the end gives you V over I. You notice that this one is actually the same as this. That's why I say that they are numerically equal. Okay, you finding gradient from origin is actually going to give you an answer similar to the ratio. Okay, so don't find gradient from tangent, find gradient from origin when you want to evaluate the resistance. Okay, it's because the gradient is equal numerically to the ratio. All right. Strictly speaking, when you're asked to define resistance and then they ask you to deduce from the graph how you know the resistance is changing, you shouldn't say anything about the gradient. Gradient is not the correct way to look at the resistance. It's just that here, right now, the correct way is to look at the ratio, right? But what I'm teaching you here is just another informal way of evaluating the ratio. This is by far the easiest one, but it's not a formal method to use. Okay, so don't make mention of gradient when you say you want to evaluate the resistance. Okay, so like in my case here, I can say the gradient from origin is V divided by I is actually going to be equals to R. But there are cases where we could actually reverse your axis, I against V, current versus voltage. So in my case here, the gradient from origin is actually I divided by V is actually the reciprocal of the resistance. Okay, so like if I see these two cases here, what can I say about how this gradient is changing? Here you can say that the gradient is dropping, right? You see it's becoming less steep. I can see that the gradient here is dropping, the resistance here is increasing. But on the other hand, if you look at the second example here, what can I say about the gradient? The gradient is dropping. Sorry. I did something wrong here. The first one, gradient is proportional to R. If gradient is dropping, R is dropping. Sorry, my mistake. And then this one here, gradient is inversely proportional to R. If I see that my gradient is dropping, my resistance is increasing. Okay. So this is how normally we evaluate whether the resistance is going to change or this is how we evaluate whether the resistance is going to increase or decrease, just by looking at the gradient of the origin. That's the quick way, but it's not a formal way to do it. It's not accepted in your marking scheme. All right. Okay, so this one is okay. Then after that, you just move on to some of the others. Okay, now then after that, we go on to IV graphs again. All right, IV graphs again. Now, you are required to know the IV graphs, voltage current graphs for 3 different components: a magnetic conductor, a semiconductor diode, and a filament lamp. Okay, they will often ask you to identify the IV graphs for these 3 components, and you're supposed to know how to draw their shapes. Okay, which is given in this page of your notes. Okay, so now you have metallic conductor at constant temperature. Now there's something called Ohm's law. Ohm's law states that current flowing through a conductor is directly proportional to the voltage across it, provided temperature remains constant. Okay, here is saying that here is saying that I is proportional to V. Okay, provided the temperature remains constant. Any conductor that behaves like this is known as an ohmic conductor. For conductor that follows Ohm's law, resistance is constant. Okay, since they say I is proportional to V, you're supposed to get a straight line that passes through the origin. And then now you want to look at the resistance. You see the gradient from the origin is always constant, so therefore resistance is constant. Okay, this is an easy way of looking at it. Now, then after that, you also have semiconductor diode. Now, a diode is just simply a device that only allows current to flow in one direction. In your case here, when it is forward bias, having positive voltage, your diode allows current to flow through relatively easily. But when your diode is reverse bias, meaning you say you have negative voltage, no current is allowed to flow. You see there's nothing here. Okay, so what do we mean by having positive voltage and negative voltage? Is something like this. This one is your diode. Okay, when you have it like this, current can flow, right? This is what we mean as forward bias. This is where you have positive voltage. Okay, now when you have reverse bias, you again still have the diode like this. But what is happening here is that you reverse your battery polarity. This one was positive, negative, right? Now this one you reverse it, you give it something like this. You reverse the polarity. This is negative, this is positive now. So basically you're getting positive, negative here. That's why we call this positive voltage, negative voltage. Okay. When you have negative voltage, you're basically reversing the polarity of your battery. In your case here, this is considered to be positive voltage, forward bias, current can flow. In this case here, reverse bias, negative voltage, no current is flowing. Okay. Now, at the positive voltages, when it's forward bias, you notice that current increases slowly and then rapidly. So this tells you that resistance decreases as current increases. Now, if you look at gradient from the origin, you can see this very easily. This point, the gradient from origin is this. This point, gradient origin is like this. This point, gradient from origin is like this. The gradient from origin is increasing, so therefore your resistance is decreasing. Because here you see gradient from origin is I over V, is 1 over R. So gradient is inversely proportional to R. If your gradient increase, your resistance drops. Okay, so this is one way to look at it. Now, then the last one you will need to know is filament length. Okay, for filament length is this one. Okay, so let me just clear off everything again. Okay, now for filament length, at small voltages, the graph is usually a straight line. Okay. At small voltages, the graph is straight as resistance remains constant. So it's actually straight initially. But then when you go towards higher voltages, the line will start to curve, like what you're seeing here. Now, the reason why it starts to curve is because when your current increase, your filament length will heat up. Because you know that when you run current through a metal, like tungsten wire that is used to make filament lamp, it will heat up. So when it heats up, it will have an increase in temperature. Okay, when you run current through it, your metal wire heats up, you have an increase in temperature. Now, the increase in temperature causes the filament atoms to vibrate more rigorously. So it will oppose the flow of any charges. Just now when we talk about resistance, we mentioned that when your charge tries to flow inside a conductor, it's opposed by the atoms of the conductor itself. So specifically now, your conductor is the filament lamp metal. The atoms are vibrating more rigorously, so it's opposing the flow of your charges. Your current will actually get less, therefore resistance has increased. Your filament lamp heats up, the atoms vibrate more, you have more resistance to your current flow, resistance would have increased. So another thing they can also do here is to look at gradient from origin again to identify this. Over here is gradient from origin equals to I over V, 1 over R. So gradient is inversely proportional to R. So again, you try to see the gradient. This one like this one like this one like this. You notice that the gradient is dropping. So resistance is increasing. Okay. So resistance increases as current increases for filament lamp. Okay. So filament lamp, resistance increase. Semiconductor diode, resistance decrease. Ohmic conductor, or rather metallic conductor at constant temperature, resistance is constant. You need to know these graph shapes. If you're asked to produce it, reproduce it, all right, and you need to know how to deduce whether the resistance is increasing or decreasing from that graph shape. Okay, so that one is okay. Then we go on to some other stuff. Okay, now this one is talking about resistors also. Now, you have two special kind of resistors inside your syllabus. You actually learned this in A2 last time, but then they've actually decided to add it inside your AS again. So now, you have something called thermistors and light-dependent resistors, all right? So both are resistors, all right? But these resistors have resistance that change with certain things. The first one is thermistor, okay? A thermistor is just a temperature-dependent resistor that changes resistance with temperature. Now, for a negative temperature coefficient thermistor, resistance decrease as temperature increase, which is why you get a graph shape that looks like this. You notice that as temperature increase, resistance drop. Okay. Your syllabus will only deal with negative temperature coefficient thermistors, meaning you say you only deal with graphs like this, where temperature increase, resistance drop. Okay. Now, change in thermistor resistance with the temperature is not linear but exponential. When your thermistor is heated, it tends to conduct more current. The reason why is because as temperature increase, the thermistor will make available more free electrons to carry current, thus its resistance decrease. You can just think of it this way. The more free electrons released because heat energy is absorbed. Okay, more free electrons released because energy is absorbed. Okay, so this is for thermistor. Now, you also have something called light-dependent resistors. Okay, so light-dependent resistor, again, is a resistor that changes its resistance with something, but here it changes its resistance with light. Okay, so a light-dependent resistor changes resistance with light intensity, with brightness. In complete darkness, it has a very high resistance of 10 mega ohm. In bright sunlight, its resistance will fall to 100 ohms. Okay, so basically you have a graph of resistance versus light intensity or brightness now. All right, when brightness increase, resistance drop. Okay, the change in resistance with intensity is not linear but exponential. That's why you get a graph shape like this. When light intensity increase, your LDR conducts more current. The reason again is somewhat similar to thermistor. When light intensity increase, your LDR absorbs more photons of light to enable more free electrons to carry current. Therefore, resistance decrease. Therefore, you can carry more current. This is for LDR. Okay, so that one is all right. Then I finally go to the last page. Okay, now this one is probably new. You probably haven't seen this in IGCSE before. Just as we learned the concept of resistance, we also have something called resistivity given by the symbol rho. The symbol rho here is the same as density, but here in the electricity chapter is used to denote resistivity. Okay. Now, if you have a given conductor with a certain resistance, what we'll say here is that the resistance of a conductor at a given temperature depends on a few factors. It depends on number one, the length L of the conductor, which is parallel to current flow. The what we'll say here is that resistance is actually directly proportional to length. The longer your conductor, the more resistance you encounter. And then the second thing you can say is that resistance is actually dependent on cross-sectional area, which is this one here. This one is your cross-sectional area A. Okay, your cross-sectional area A is perpendicular to current flow. Okay, so what can you say about resistance and cross-sectional area? You can say that resistance is inversely proportional to current. Wait, resistance is inversely proportional to length, sorry. Okay, there's something wrong with what I wrote here. Okay, sorry, now I just realized it. Resistance is inversely proportional to cross-sectional area, 1 over A. Sorry, I noticed that there's a mistake here. Resistance is inversely proportional to cross-sectional area. So what you can say here is that when your area drops, your resistance ought to increase. When your area increase, your resistance drop. That's why we say that it's inversely proportional to cross-sectional area. Okay, so these two factors affect resistance, length and cross-sectional area. Another thing that could also affect resistance is the material type that contains the mobile charge carriers. All right, there's a particular physical quantity that relates to this, right? But to get that, you have to relate these two other parameters together. So just now we say that R is proportional to L and R is inversely proportional to A. If you combine those two relations together, you will get R is proportional to L over A. You want to get rid of the proportionality sign, you introduce a constant rho. Then you get R is equals to rho L over A, where rho is the resistivity measured in ohm meter. It's a measure of the resistance of the material. Okay, and then this one is good. It's a better measure of your resistance because it's constant for any given material type, regardless of its size and shape. It's something like Young's modulus. If you've done deformation of solids before this, we will tell you that Young's modulus is a measure of stiffness of the material. and it's a better measure of stiffness because it just depends on the material. It doesn't depend on its size and shape. So it's a similar analogy here. Resistivity gives you a measure of the resistance, and it just depends on your material. It doesn't depend on the size and shape, right? So this is resistivity. Okay, then I'll fill all. Then we go to the last part, power. Okay, power should be very fast. Now, power, is rate of work done or rate of energy change. So in an electrical circuit, electrical power is the rate at which electrical energy is converted into other forms of energy. So there are three equations that you need to know for power. Electrical power P of a device is P equals to VI, okay? And then since you know that resistance is R equals to VI from the previous page, I is therefore V over R, or V is equals to IR. Now, if you look at this equation 1, if you substitute for V, you get Pi times IR, giving you Pi square R. And then after that, if you again refer to equation 1, now you substitute for I, you get P equals to V over R times V, you get V squared over R. These three equations will be used normally to calculate power dissipated in an electronic component like your resistor or your lamp. Okay. Now, specifically for a cell or a battery, the power generated can be found through a similar equation in 1, where instead of using P equals to VI, we use P equals to EI, where E is the EMF. The equation 1 that you have here is using V, PD. This equation here is using E, EMF. Okay, and I is the current through the cell. And then eventually what we can also tell you is that because of conservation of energy in an electrical circuit, power generated at the cell is equals to total power dissipated at resistors. Okay, so that is for this. Okay, so we've done this entire concept for electricity already, the basics one. So maybe we try to do some questions from there, right? Or do you need a short break? Okay, no, it's all right. Okay, so let's try and do some short question. Resistivity. Okay lah. Maybe we try and do a mix of everything. Okay, let's have a look at page 77. Okay, we have a look at page 77. Okay, so let's have a look at page 77. Okay, the current shown in circuit is 3.2 milliamps. What are the directions of flow and rate of flow of electrons through resistor R? Okay, so they want the rate of flow, they want the direction of flow. Rate of flow here refers to the number of charged particles per unit time, because you see it's per second. So what you learned was I is equals to Q over T is N Q over T, giving you N over T I divided by Q. Okay. Current is 3.2 milliamps, change to ampere, so times 10 power minus 3. Now charge of an electron is actually negative E, which is negative 1.6 times 10 power minus 19. But you don't really need to bother about the negative sign here because we're really just interested in the magnitude. So this is 1.6 times 10 power minus 19. 3.2 times 10 power minus 3 divided by 1.6 divided by 10 power minus 19. You're gonna get 2.0 times 10 power 16. This is number 1. Okay, you can either be this or this. Now, then after that, notice that the one electron. So if you're talking about direction of conventional current, it flows from your positive terminal to negative terminal. This one is conventional current, the current that we always use. But the question wants electron, you see. So one of the first thing I mentioned to you is that electron is always opposite to conventional current. Electron flow, which is a negative charge, is opposite to conventional current. So rather than flowing counterclockwise like this, electron is supposed to flow like this. Okay, this one is electron flow. Maybe I should just highlight it. This is electron flow. Okay, so it's supposed to flow from Y to X instead. So your answer here is D. Okay. Hey, sorry, not D, not D, sorry. 2 times 10 power 16, right? C. Answer is C. Because it needs to be 2 times 10 power minus 16, and it needs to be from Y to X. So answer is C. Okay, 2 times 10 power 16 from Y to X. So this is for current. Okay, so this one is all right. Then after that, I'll just clear off this one. All right. Okay, now which graph best represents the way current through a filament lamp varies with the potential difference V through it? So you see, this one here, if let's just say you memorize the graph shape, that one would be good. But then I won't suggest you memorize the graph shape. Just now the graph shape for filament lamp was this, right? This is I versus V. Sometimes the question may try to play tricks on you. Rather than giving you an I versus V, they may just give you V versus I instead. So then the graph shape will change completely. It's actually flipped. So I won't suggest memorizing the graph shape. I will suggest looking more towards deducing from the graph whether resistance is changing to be larger or smaller. Okay, so one of the first thing you remember for filament lamp is that resistance increases as current increases. This one is what you know for filament lamp. Now then after that, the gradient from origin, don't take the tangent, is I over V, which is 1 over R. So gradient is inversely proportional to R. If your R is to increase, gradient must be dropping. This is number 2. Gradient from origin must be dropping. Okay, so you look at this one. For filament lamp, you remember the shape is either these two. This one could be more for ohmic conductor. This one could be more for diode. So it's either these two. So you want to be certain which one is which. So this one, you just draw something like this. Look at how the gradient changes from the first point to the second point to the third point. Notice that the gradient here is increasing. So resistance here is dropping. But then you do a similar analysis for the answer choice B. You notice that this gradient is dropping. So resistance is increasing. So answer should be B, which is what you're actually seeing in the notes. Graph of I versus B looks like this. Okay, so answer is B. Okay, then we move on to question 35. Okay, question 35 is talking about your resistivity. So let me just clear off everything. Okay, so I'll clear off everything. Okay, now you have a cylindrical metal wire X of resistance R. the same volume of the same metal is made into cylindrical wire Y of double the length, what will be the resistance of wire Y? Okay, so there are a few things here that are of interest to you. Specifically this one, they told you it's same metal. When they say it's made of same metal, that means it has same resistivity. Okay, so same resistivity, and then this one here, they told you it has same volume. Okay, yeah, same volume. So what is the resistance of wire Y? Okay, let's go with the case where we're talking about volume first. If say you have a conductor like this with length L and cross-sectional area A, remember I told you volume is area times length, but now they tell you volume is constant. So constant volume would mean that A is inversely proportional to L. So if you have double the length, L increase 2 times, A will reduce by 2 times. Okay, this is the one relation you know. Okay, now we go to the actual finding resistance part. Okay, I'll draw it at the top. Whenever you see questions that make mention of length or cross-sectional area, you know for sure most of the time you're going to be using this already. You had two different equations for resistances now. R is equals to V over I, or I is equals to rho L over A. One way to know which one is supposed to be which, you see the question, if they make mention of length or cross-sectional area, most of the time it's going to be rho L over A instead, not V over I. Okay, so now you have I is rho L over A. If you're talking about same metal, so same metal, that means rho is constant, R is proportional to L over A. Okay, this one you know. Okay, so now you want to evaluate the changes. Let's just evaluate the changes one by one. If L increased by 2 times, that would mean that R increased by 2 times. This is the effect of L alone. But what about the effect of area? Area, you already know it should have decreased by 2 times. So area is decreasing by 2 times. But because this is an inverse relation, if this one drop, the other must increase. So R must also increase by 2 times. So now you see, due to L, R increased 2 times. Due to A, R also increased by 2 times. So your conclusion is that, therefore, overall, R increases by 4 times. So it should be 4R. Therefore, okay, so Ry will be 4R. Just like this.